Hello everyone, thank you for coming. This is Ikuo Katayama speaking from Hiroshima. So can you see two planets? The left side planet is, of course, this is Earth. And what is the right side planet? So this is Mars. And of course, many difference between Earth and Mars. But the biggest difference is the water, the presence of oceans. So the Earth is blue because of covered by oceans. Mars is red, dry, and no oceans, at least at present day. However, many of you know the water, possibly oceans, has been existed in the early histories of Mars. So this is outflow or channel in the Tarsis Valley in Mars. And this is lake-like deposit we can see from rover at Gale craters. Maybe the water is taste of noodles or ramens, as Fukushi-san suggested. Anyway, so the possibly the water, liquid water, maybe oceans, existed in the early histories of Mars, but it disappeared. So where it goes? So this is the questions. First, I want to discuss in this talk. And on the other hand, the water in Earth, the ocean, seems to be sustainably existed throughout the geological history of Earth since probably since 4 billions of years ago. And this long-term existence of global ocean is very, very essential for not only for origin, but also evolution and development of life, right? So the question is, what makes such a sustainable existence, stability of ocean throughout the geological history? So this is another question, okay? So in this talk, I will discuss following two questions. Of course, I don't have a good correct answer yet, but I want to discuss these issues. First topics is how ocean disappeared in Mars, and the second one is why ocean is stable in Earth throughout the geological histories. Okay. So first topics, oceans in Mars. So based on topography that is obtained by remote sensing like Mars Global Surveyor indicates the northern hemisphere of Mars are characterized by smooth and relatively low elevations. And possibly the oceans covered existed in these regions, in these northern lowland. And the equivalent volume of oceans is estimated to be something like 150 meter thickness of oceans, that is global equivalent radius. But this ocean has gone. And possible scenario for the disappearance of ocean is such water or ocean escape to the space because of relatively small gravities in Mars, as evidenced by enrichment of deuterium in the present day Mars atmosphere. But these isotopic signatures indicates the water loss to escape is limited something like a 50-meter thickness global equivalent layer. And what about remaining 100-meter water oceans? And possible case is these waters might be escaped, not escaped, might be sucked and stored in the interiors of Mars. Okay, so the possible answer for this first question, how ocean disappeared in Mars, our hypothesis is the ocean might be sucked and stored in the interior of Mars. And how to test these ideas? So we focus on elastic thickness. That is mainly controlled by rock rheology, rock strength. That means the elastic thickness is very sensitive to the presence or absence of waters. Okay, so using these sensitivities of elastic thickness to waters, we test this hypothesis. Okay. So they are based on topography and gravity's anomalies are reported in Mars. The regional variations of elastic thickness, a number of elastic thickness in various locations has been reported. And these observations indicate the elastic thickness in Mars tend to increase with age. The younger age are characterized by a relatively thick elastic layer compared to the old locations. And this age dependence of elastic thickness can be explained by the secular cooling because low temperature, less abundance of radiogenic elements, low temperature in younger age result in stiff lithosphere. That means thick elastic layers. Okay. However, the reported very thin elastic layer in Noachian's very early history of Mars, these very thin elastic thickness cannot be explained by temperature alone, and possibly we need water to explain these very thin elastic layer in the very early history of Mars. Okay, so what controls the elastic thickness? The elastic thickness is actually mainly controlled by strength of rocks. That means rheological structures. Okay, so this is the strength envelope of lithosphere in which the shallow parts of lithosphere is mainly controlled by brittle deformations, and the lower parts of lithosphere is controlled by ductile and plastic deformations. And the elastic thickness, this TE, can be calculated from these rheological structures. So that means if we can calculate, we can make this strength envelope from the models, we can estimate elastic thickness and compare to the observations. Okay. And the water has a significant influence on the strength of rocks. For example, the presence of water substantially reduce the friction resistance, like this. And also water dissolved in the crystals weaken the ductile strength, like this. So the rheological structure, rock strength, is very sensitive to the presence or absence of water, and we expect a thin elastic layer under the presence of water, under the water-rich conditions. Okay. So, okay, to compare to explain the variations of elastic thickness reported in Mars. We calculated elastic thickness based on the rheological structures, including the crustal thickness, radiogenic radioactive elements as heat source, and geological age according to the distribution of craters. And we calculate elastic thickness of various locations in Mars to compare the observations. And in this talk, I will show 3 examples. The Northeast Arabia Terra is the oldest location. You can see many craters here. And Pavonis Mons, that is kind of a volcano. This is the youngest location. Okay. So this is calculated rheological structures of 3 locations, 3 different locations in Mars. From left to right are getting older. So the oldest locations are because of relatively high temperatures, the strength is relatively weak and the elastic thickness is relatively small compared to the younger and colder terrains characterized by a thick elastic layer. So first, elastic thickness is depending on the age of locations. But this is calculated under dry environment, but what about the effect of waters? So these are the results of rheological structure calculated under the wet environment, and elastic thickness calculated for wet environment is much thinner than the dry environment. So the elastic thickness is very sensitive to the presence of water, and water-rich environments we expect thinner elastic layers. Okay. So this is the summary of elastic thickness, calculated elastic layer in various locations in Mars. From the bottom to the top are getting younger. So the first, the result under wet conditions, again, this is much thinner elastic thickness compared to the dry environments. This is very unique characteristics. And compared to the observations, observed elastic thickness in Mars from the topography and gravities data, the most observations in the younger age, like Amazonian to Hesperians, can be explained by the dry models. But the elastic thickness reported in the Noachian very early history of Mars are consistent with wet models. So we, based on this result, this calculation and comparison to the observations, we suggest the wet lithosphere has been changed to dry environment through the Martian history. So at least we have evidence of waters in the interior in the very early histories of Mars. Okay. So to answer the first questions, how ocean disappeared in Mars, so our tentative, not final, but the tentative answer is such water, part of such water has been stored in the interior of Mars, according to the sensitivity of elastic thickness to water and reported extremely thin elastic layer in Mars. And these ideas can be further tested by ongoing missions called InSight, which recently detects number of earthquake, kind of Marsquake, sorry. So seismicity in the Mars is they call Marsquake, not earthquake. So this is, if, the rock rheology indicate, the distribution of seismicity, Marsquake is very sensitive to the presence of water. If the dry environment in the interior of Mars, we expect distribution of seismicity can be expanded to deeper portions, but under the wet environment, seismicity's Mars grip can be limited to very, very narrow, very shallow portions. So if this project InSight can determine the distribution of not only the detection of Marsquake, but distribution of Marsquake, we will see the presence of water or not in the interior of Mars, at least the present day interior of Mars. Okay. So, okay, let's move to second topics, the oceans in Earth. The sustainable existence of oceans in Earth are possibly two reasons. The first requirement is the climate stabilities at surface, because the liquid water is only stable at temperature between 100 and 0 degrees C. Above 100 it evaporates, and below 0 degrees C it will be ice will be dominant. So we need a very narrow temperature conditions throughout the geological histories of Earth, like 4 billion of years. How does it work? And the second requirement is water budget, balanced water budget in the interiors, because water is not only circulated at the atmosphere, but also circulated, transported, and adapted in the interior of Earth. So this is another requirement. Okay. So first requirement is the climate stabilities. So the liquid waters might exist much stable in the early history of Earth, not only Earth, but also Mars and even in Venus, according to the carbon dioxide concentration, carbon dioxide and the planet radiations. But the liquid water was only stable in Earth throughout the geological histories. The Venus, because of runaway greenhouse effect, water has been evaporated, most of water, and Mars is too cold at present day, and liquid water is not stable anymore. So how does it work? How maintain the stability of water throughout the geological history in Earth? That is possibly due to the decreasing and maintaining carbon dioxide, right? And this is most likely due to the operations of plate tectonics. The plate tectonics, subductions, eruptions, and the weathering, and these global cycle of carbons makes control the level of atmospheric carbon dioxide and make the Earth's surface stable throughout the geological histories, but not as a planet because of absence of plate tectonics in other planets. So this is first requirement, operation plate tectonics. And another requirement is the waters. Similar to carbon dioxide, carbon cycle, so water is also circulated in the interior of Earth. And a recent estimate of a water budget, present day water budget, shows the water input by subductions is slightly larger than water output by volcanic eruptions. And this means, at least present day, the input is larger than output, and that means the volume of oceans will getting down, possibly. And even more, recent geophysical observations has shown extensive hydrations along these outerized regions, bending-related faults. You know, the plate bended at the trench, and hydrations can occur along these normal faults, and seawater can be infiltrated. And this means so much larger input water can be trapped in the oceanic lithosphere and transported into the interiors. So how much water actually trapped in the oceanic lithosphere is key for global water cycles, right? And to make a quantitative estimate of water in the oceanic lithosphere, we are measuring seismic velocities in laboratories of various rock samples, such as serpentines, hydrations, products of mantos at conditions in the mantos. Okay, so what we found from the laboratory experiment is the seismic velocity. For example, P-wave velocity is very sensitive to the water content. And if we know the P-wave velocity down to 6.5 km per second, for examples, the water content in such location is something like 7%. So based on these relationships, we can precisely estimate water content compared to in comparison to the geophysical observations. Okay, and our rough calculations of how much water is trapped, including this outerized hydration, is this amount. This is twice as high as previous estimate. And this means a much larger amount of water is now transported in the interior of Earth, and simple calculations are volume of oceans divided by this rate indicates the ocean can be disappeared within the next billions of years. So this is rough calculations, but at least the water budget is not balanced at present day, and the oceans in Earth may be disappeared in the future, similar to Mars. Okay, so to further test these ideas, so how much water are actually trapped in the oceanic lithosphere is key to understand the global water cycles. And this can be explored by the MOHO project, that is drilling through the crust to mantos, and possibly by the drilling vessel JpGU. Only JpGU can be able to drill such deeper part of Earth and tackle to the mantos. Okay, and we are now starting many ongoing project to drill across the crust mantle boundaries. So this is Oman drilling project that is drilling across the crust mountain boundaries of the biggest ophiolite in the world, Oman ophiolite. And you are always welcome to join these projects anytime. Okay, so this is, so to answer the second questions, why ocean is stable in Earth. So most likely because the water budget has been balanced throughout the geological history, but not present day. And present day water budget indicates the ocean might be getting decreased and possibly disappeared in future, similar to Mars. Okay, thank you for listening. That's it.